Hello everyone, thank you for coming to my talk about Tech Art and Shattered, a mixed reality escape room game. My name is Rohin. I'm a programmer and technical artist with over 10 years in the games industry. I've previously worked at Pickpock, Maria and Playside, where I worked on Civilization 7 VR and Shattered. I'm currently at Beast Burst Entertainment, developing Scars of Honor, which is an MMORPG. So, what is Shattered? It's a mixed reality escape room thriller built by Playside Studios for the MetaQuest 3. The game transforms the player's real environment into part of the experience, pulling virtual objects into your room and opening portals on your walls. I worked on this game last year with several other tech artists. It was the first mixed reality game I worked on, and there were a lot of technical challenges, especially around some of the performance optimizations. And I'm excited to share some of the techniques we used to solve those challenges. First of all, placing items. In Shattered, there are two types of items you can place in your room. The first are room-anchored items, things that you place using the reflection system, like desks, doors, or walls. So these are basically, thank you. These are, can be interactive, basically like a desk where maybe you have to open a drawer. And the second type are like pickup items, things you can like move freely and you can throw across the room, like that vase on that table. To support both systems, the programmers built a room mapping system. The system ensures like tables like virtual items like tables can be placed at the player's floor, and pickup items can be placed on either virtual surfaces or real-world surfaces. So that vase could also be placed on the player's desk next to them. Custom dynamic lighting. So the biggest challenge was probably getting custom dynamic lighting to work smoothly, run at a smooth FPS. We needed the game to run at about 72 FPS. This was to ensure the experience was smooth with no motion sickness and to align with the default refresh rate set by Meta. So we made the decision early on to avoid using Unity's dynamic lights. We instead used three techniques: LUT blending, lightmap and light probe switching, and custom lighting and shader code for the torch effect. LUT blending. First of all, what are LUTs? LUT stands for lookup table in game development. It's a texture used for color grading, styling, and tone mapping. It works by remapping input colors to new output colors. On the right, you can see an example from Rocket League before and after a LUT has been applied. And below is an example of a neutral LUT texture, which represents unmodified color values. The usual workflow for creating a LUT in games is take a screenshot, bring both the screenshot and the neutral LUT into Photoshop, make your color adjustments, and then export the adjusted LUT as a new texture. Normally, you would use a single LUT, but you can also blend between two LUTs at runtime to create dynamic lighting effects. There are different ways to store LUTs, but the most common is 2D and 3D textures. We used 3D textures for room extensions and virtual objects, and this is because 3D textures are easy to work with and provide better interpolation quality. Unity supports these through the texture 3D format, and also shaders can sample them directly. And for the pass-through shader, which is the real-world camera feed of the player's room, we used 2D textures. This is because the pass-through is a fixed function shader and it cannot be modified due to privacy reasons. The good news is this shader does support blending between two LUTs at runtime to create dynamic lighting effects. And here is an early prototype where we were experimenting with blending between two LUTs to give a dynamic lighting effect. Next is a light map and light probe switching. First of all, what are baked light maps and light probes? So baked light maps are textures that store pre-computed lighting for static objects. They're great for performance because all the heavy calculations are done ahead of time. And light probes store sampled lighting at points in space. Those samples are interpolated to light dynamic objects. This way, moving characters feel grounded in the baked lighting environment without expensive runtime lighting. Unity provides a straightforward workflow for baking light maps and placing light probes in a scene. But if you want to switch light maps and light probes at runtime, you need to create your own solution for that. And thankfully, it's fairly straightforward. So by default, Unity saves only one baked light map, baked lighting setup per scene. But with code, we can save multiple lighting setups in the scriptable objects and switch them at runtime. Now, the number of scriptable objects you need depends on the situation. If it's just a room where all the lights are either on or off, then you only need 2 scriptable objects. But if the room has lights that turn on and off independently, then you need, say, multiple scriptable objects to cover all lighting setup permutations. So the game Gone Home probably does something like this, where you can go through this empty house and switch on different lights independently of each other. And here's an early prototype of it being used in game. There is a cube placed below the lights, and although it isn't being like animated or anything like that, it is actually a non-static object which is being lit by the light probes. And I just want to mention, we did use Bakery, which is a GPU light mapper, mainly because it fixes common baking artifacts such as like light leaking. But the process for swapping light maps and light probes at runtime is mostly the same, regardless of whether you're using Bakery or Unity's light mapper. The torch. The torch is an essential tool that you use in every room. It lights up dark areas, and it has a blacklight mode for revealing puzzle clues. And for the torchlight, we basically we based our calculations on the spotlight technique from Lightcaster's section on learnopengl.com website. Any surface that could receive torchlight needed the same custom lighting code included in its shader. This ensured that all surfaces responded correctly to the torch, no matter which shader was being used. And the torch game object had a script on it that updated global shader variables each frame, keeping the torchlight position, rotation, and color correct. There's also some global variables for the torchlight cookie, and I think the light attenuation was fixed, was hard-coded. And here's an early prototype of the torch in action. So apart from the lack of shadows being cast, it looks very similar to a Unity dynamic spotlight. Room extensions and stencil masking. In the game, you have a main room extension and then a secondary extension, which could be a door, a hole in the wall, or a trapdoor in the ground. We use stencil masking to ensure objects viewable in an extension are only visible inside that extension and not elsewhere. So, first of all, what is stencil masking? Stencil masking is a way for the graphics card to decide which parts of the screen should be drawn, which parts should be skipped. Each pixel can have a small number stored in a stencil buffer, and shaders can check this number to know whether to render that pixel. This lets you mask effects without changing your object shapes. Think of it like a stencil for coffee art or painting. Only the areas inside the stencil show the effect, while everything outside stays unchanged. In games, this is used for things like portals, mirrors, outlines, or layered visual effects, letting you control exactly which visuals appear. There are two main ways to use stencil masking to control which geometry is visible. The first method uses the stencil to draw a camera's view. Games like Portal or games with like security camera monitors use this approach. The stencil defines the portal shape and a separate camera renders the view inside that area. The second method uses the stencil to reveal hidden geometry. Games like Antechamber use this technique. In the example on the right, all the shapes occupy the same space, but you can only see one at a time depending on which stencil mask you are looking through. In Shattered, we use the second approach. Here is an example of a main room extension being opened. All the geometry is first loaded, and then the shader draws a stencil mask which reveals it. And another example, in this example, a player has placed a door in front of a room extension and opened it. Each portal has a separate stencil mask ID, so the door uses a separate stencil mask ID from the one used in the room extension. This means geometry that is viewable behind the door is only viewable when looking through the doorway and not inside the room extension. Early on, there was like a bug where some geometry would appear where it wasn't supposed to. The problem was this geometry was using an older shader at the time, and it was getting the wrong stencil ID set to it. So when you look into the room extension, sometimes you would see something floating in midair that didn't belong there. Next is mirror cracks. So in one of the rooms, we needed cracks to grow on a large mirror. The mirror consists of two transparent pieces of geometry, a glass mesh, and a cracked mesh that sits just behind it. Depending on the situation, the crack had to either grow uniformly from the center or grow along the middle first and then outward to the edges. To achieve this, we experimented with two different techniques. The first technique we tried was a distance-based reveal. There was a shader parameter to represent distance from crack origin, and we updated every frame. For each pixel, the shader would either show or hide it depending on whether it was within that distance. For the first crack, distance was treated as radius, while for the split crack, it was based on x and y coordinates. But this approach had some problems. It looked obvious it was a circle or a box mask revealing the crack, and during the reveal, some parts of the crack became visible before they were connected to the origin. In this example, you can see in the bottom right part of the crack, it's not yet connected to the main crack part during the reveal. Because of these issues, we moved on to try a second technique. In the second technique, it was basically using vertex color, so vertex color-based reveal. In this approach, the shader reveals the crack based on vertex color. Each vertex on the mesh stores a color which the shader reads to determine visibility. In Blender, we wrote a script that starts from a selected vertex and performs a flood fill across the crack mesh, assigning weights to each vertex as it spreads outward, and then these weights are normalized and stored as vertex colors. For the split crack effect, the script was updated to perform a two flood phase. First, flood fill a group of vertices and then fill in the rest. With this setup, we could, the animation could be driven in the timeline using a 0 to 1 float parameter in the shader. And here's what the result finally looked like for both types of crack. On the left is the one which is uniformly fills, and then on the right is the split crack effect. And here's an example of it being used in a game. There are actually multiple parts to this effect. There's the growing cracks, and then the shards of the mirror fall out, which is another technique where we swap it for the actual shards that fall down. And there's also a stencil effect being used here. Each side of the split has a stencil mask, and I guess it helps tell the story of how this poor character is being turned into a wraith. Next is a glass shatter effect. So in the game, there are some places where we need to break some windows. This involves smashing glass with a hammer until it shatters, and then simulating glass shards falling to the ground. For the glass shards falling to the ground, we simulated it in Houdini, and then stored the baked animation data in textures. These textures are called vertex animation textures, or VAT for short. The pixels along each row translate to vertex positions, and the row being read depends on the animation frame number. You typically need 2 textures, one for vertex positions and one for vertex rotations. Each pixel translates to XYZ for position or rotation. And this is what baked textures look like for the glass shards. But we ran into a problem with the bat shader approach. The simulation was baked in Houdini with a fixed height from the ground. However, a player could place the window at any height from their floor. This meant the glass shards would either fall through their floor or end up floating above their floor. There were several solutions to this problem. We could restrict the placement of the window so the user could never place it up high or down low. We could update the shader to fade out the shards at the end of the simulation before they hit the ground. But we really wanted the shards to always land and stay on the player's ground for the player to be able to, place the window at any height they wished. Now, if we just scale the bounding box height of the simulation, a low window would mean shards break and fall too slowly, and a higher window would mean shards fall too quickly and don't burst outwards first. So this is the solution we ended up using. It's a bit hacky, but it works using smooth step and lerp. So we're using smooth step and lerp. The start position of the animation still looks correct, and it bursts outwards, and then the shards still fall correctly to the ground at the correct speed. And here's an example of it in game. There are 3 parts to this effect. The shadow mask gets placed at each location you strike the glass. There is a particle effect that plays with each strike. And then the VAT animation is played to simulate the glass shards falling to the ground. And something really cool, if you remove that broken window and then place it back in your room at a different height, the shards will still be at the correct location on your ground, on your floor. So yeah, it was quite an achievement. Next is shader plumbing. So we had the following problem. We need all our lit shaders to have a custom code for things like the LUT blending and the torch effect. This had to run inside the final vertex and fragment functions. And we're using ShaderGraph at the time. Now, unfortunately, there's no official solution by Unity for extending ShaderGraph this way. The good news is there are some unofficial solutions, and we end up using a solution on GitHub by Zealous called Unity Universal ShaderGraph Extensions. This solution allows us to inject LUT blending and torchlight code into the lit shader. The only problem is it requires a lot of plumbing. And in the end, we decided to convert most of our shaders over to Amplify Shader Editor. Amplify has a template system that exposes the underlying shader structure, so you can choose exactly where your custom code goes. And this was basically the main motivation for making the switch. And it is common for a project to start using ShaderGraph at first because it comes with Unity, but then run into issues later due to limitations of ShaderGraph, and then end up having to either write their own shaders from scratch or switch to Amplify. And following some unused prototypes that we didn't end up using, we were once experimenting with having cracks suddenly appear on the player's wall and opening up, and like water rushing in and drowning the player. For the crack effect, we have the crack mesh that we animate opening using blend shapes. And on top of the crack mesh is a stencil mask, which also uses the blend shapes to open up. And the most important part is the crack mesh and the stencil mask mesh need to have exactly the same blend shape animation to ensure front-facing polygons were only ever visible looking into the crack and not from the side. This is a prototype where we're experimenting with adding dynamic light luminance to create light flicker and dim effects. This code would run in the shader after the LUT blending calculations, and it was extremely cheap to run, but we didn't end up needing it, but it's another option if you want to create fake dynamic lighting. And at one point we're experimenting with blending between 4 LUTs instead of 2, and this was to offer a calibration option at the start of the game, letting players set a custom neutral LUT, similar to how horror and atmospheric games let you calibrate the black and white levels. In the background I've placed 3 options of different colours, and I may have also placed that cat there. And this is one of the earlier cracked mirrors. Some of the shader techniques used are adjusting the emission of the cracks based on the viewing angle, and the scrolling UV technique is used for the light rays. Also, something interesting about the game, the designers had originally built the game to be mostly a VR experience with the occasional mixed reality room added in at some places, and then later on the decision was made to switch to make it a full-on mixed reality game. But I remember playing through some of the original gameplay levels when it was still just mostly a VR game. There was some really interesting levels that had been fully built and textured and everything. One where you had to poison a chef to sneak past him. Another one where you had to create a distraction in an asylum common room to sneak past a guard. Hopefully, if one of the designers saw some of this content, they will one day give a talk about this. And that's the end of my talk. Thank you so much for coming. Are there any questions?
Hey, Rohin. Interesting stuff. I was just wondering how you did the volumetric looking light on the flashlight. If you could talk about that, that'd be great.
Good question. Yeah, I forgot to mention that. We did use a third-party asset for that.
It wasn't AVL, was it?
I can't remember what it was called, but yeah.
Hi. Sorry, I was wondering for the mirror shattering effect, why didn't you just use decay materials?
Good question. I'm not sure. I think, yeah, I don't think we looked into that at the time. I guess with decay materials, could we have still done a 3D effect where the cracks were fully 3D behind the glass?
Yeah.
Okay, yeah, I don't know why we didn't look into that then. That's, yeah, good question.